Hi, this is Chemistry 111, experiment number 6, dissolution kinetics of solids and applications with spherical candies. Well, the basic idea is we're going to take some hard candies, throw them in water, and learn something about the kinetics, the rate at which they dissolve. We're not going to go for some simple calculation of, I don't know, mass lost over time, something like that. We're going for the Arrhenius activation energy for the dissolution of this spherical candy. Now, that's a somewhat obscure value to go for, but it's something that's important in the pharmaceutical industry, and that's what we're shooting for. Now, rather than start with calculations, which we're really not going to be using directly anyhow, we're going to go right to the procedure this time. So grab a 1-liter beaker, put some room temperature water in it. I'd say, who knows, about half full should do it. Clamp a thermometer to that so that you can record the temperature at any time. Get ready to add a massed hard candy, and when you throw it in, hit a timer and see how much of it is left after 2 minutes. So you'll be stopping the timer the second you take it out of the water, blotting it dry, putting it on a pre-weighed weighing boat since it might be sticky, and bringing it over and finding its mass. Then you bring it back into the water, hit the start button the second it enters to solution, and in that way hit start again. You don't have to hit restart, and so now you're going up to 4 minutes. Get it? It's already been exposed for 2. So 2, 4, 6, and 8 minutes at room temperature. Then we do the same thing at 10 degrees, 30 degrees, and 40 degrees. We're going to do this by just using cold water and hot water from the tap and adjusting as necessary with little pieces of ice if you need it, or with hot water if you need it. And you'll manually try as best you can to maintain a constant temperature water bath. Okay, once you get all those values, you'll plot the cube root of the candy mass versus time. We'll have a little bit more about that in a minute, and use 4 sig figs for that. And so that's what that graph looks like here. The cube root of the mass at each of those 4 points versus the time in seconds. 2 minutes, 4 minutes, 6 minutes, and 8 minutes. But use seconds, please. The slope that we get will be equal to the negative value of the rate constant. Remember, the rate constant should be a positive value. We'll use 3 significant figures for the slope. That's fine. And then take that data, and once you have your natural log of k data, plot that versus the temperature data. This should give us a single slope. You'll, I believe, get 4 points. For this one, you will get a k value for each temperature. You'll be printing out all 4 slopes on one sheet. For this one, we'll get a single slope, and that slope is equal to the negative value of the activation energy, which you'll recall is what we're shooting for, divided by the gas constant, which is 8.314. There it is. I hope you can see it, joules per mole. And we'd like you to give the final data in kilojoules per mole. So to go from E sub A divided by R in joules per mole, and then to convert it to kilojoules per mole, you should have enough data to do the conversion there. Okay, that's the basic idea. Here's some handy notes. There are some rather obscure formulas that go into this, especially this one. Check this out. This is the Hickson-Crowell cube root law for the dissolution of spherical solids. I'm thinking that only people that deal with pills really would have to obsess over something like this. We don't have to use this formula directly since we simply plot this versus that, and the slope is equal to the negative rate constant. But here it is, and I'll go ahead and quote it briefly. That's why we need to use the cube root of the mass. The cube root of the mass is equal to the original cube root of the mass minus the rate constant times the time in seconds. So this would be the mass that's left after a certain time of dissolving. This would be the mass that you started with. Fine, and it's at a constant temperature. So that's why we use this to get that slope, which is the negative value of the rate constant. But what we really want is the activation energy, and there it is there in the Arrhenius equation, which is the natural log of that rate constant, which you got here, is equal to the negative value of the activation energy divided by the gas constant times the Kelvin temperature plus the natural log of a value A, which we won't use at all, but in case you're curious, it's the y-intercept. We don't need to use this formula because once we have K and we know the temperatures, we can simply plot the natural log of K versus 1 over the Kelvin temperature and get the slope, which can then be converted into the activation energy. Got it? Hope you do. Here's some handy hints in order to get good numbers. I would think that the most common source of error in here would be either you messed up your calculations, and that's why I'm trying to help you with them here, show you some details, or you just weren't precise enough when you did your measurements. So here we go. Be as precise as possible for the times, which I think you could probably think of some strategies for making that as accurate as possible. Don't start the stopwatch until the second that the candy enters the water. Don't stop the stopwatch until the second it leaves the water. That's probably a two-person operation. One person with tongs to pull it out, another person to hit the stop button the second it leaves the water. The temperatures will be another challenge in that we're just manually trying to maintain a constant temperature. If one of your experiments goes really bad and you have a large temperature variation and you know it, consider just repeating that trial. And the masses, well, the stuff is going to be sticky, so if you consistently blot it to the same amount and you consistently mass it using the same procedure, that's probably the best you can do. Use hot and cold water, and that's it and a little bit of ice if you need it for maintaining those constant temperature baths. Don't use any external heat or hot plates, anything like that. If you use a weighing boat for massing the candy, you might be better off, especially if you have one nearby for when you transfer it to the balance so this gooey mess doesn't get all over the place. Remember to use seconds here, not minutes. Stop the stopwatch exactly when the candy leaves the water. And don't reset the stopwatch. You can just keep a running time, to go from 2 to 4 to 6 to 8 minutes. Just use start and stop. Oh, do reset it for each new candy. Transport the candy on that pre-weighed boat. That's nice for you and it's nice for us so there's not goo everywhere. And here are the calculations we'd like to see. Now, since this isn't like plug into a formula, it's more just a lot of tabulated data. So what I'll be asking for is 3 tables here. A table where you have each of your masses and then list the corresponding cube root of those masses so we can make sure those look good. A degree Celsius, degree Kelvin table where every time you have a Celsius temperature, show me the Kelvin, and a Kelvin to the natural log of Kelvin table. In other words, the calculations you'll just be doing over and over and just plugging them into your calculator. It should be pretty easy to see if you've done them all correctly or if there's errors by showing me these tables. But do a conversion with a mathematical calculation for me when you show the conversion of the activation energy divided by R, which is right there. See how it's the negative value of that slope? And convert that to the activation energy in kilojoules per mole. Here's the data you need to convert that. Okay, that's the experiment. I hope it goes well for all of you. There will be no post-lab questions for this lab, yay. And for next week, let's make the quiz open notes. Similar questions to the type you've seen all along. And in this case, I think we will go open notes.